Assalamu alaikum. Let's start lecture 20 of CS 218 Data Structures and Algorithms. Our topic is trees, chapter 13 of book 1. In the last lecture, we were introduced to the tree structure. We learned about the terminology associated with trees. We learned about the binary tree. And we learned to classify binary trees. Let us start with a class definition for the binary tree called the B-tree class. This is in the file called binarytree.py. First, let us look at the init function of the class. The init function takes pointer of the object that you have created and it creates a node containing three fields: data, LC, which stands for left child, and RC, which stands for right child. In addition to pointer to the object, you are also providing the init function a value called item. So it sets this value in the data field and initializes the left child to none and the right child to none. Now you have a node of the binary tree and it is being pointed to by self. Time taken to create this node is constant. So it is O1. Add LC. This function adds a left child to a node pointed to by self if the node does not already have a left child. Look at this node. I want to add left child to this node. Now this node itself can be either right or left child to its parent. I don't know what kind of child it is. So the incoming arrow to the node is straight. But that does not change anything for us. And in fact, this information is not required, whether this node is the right child or the left child. This node may or may not have a right child, and we are not bothered with that. What we are concerned with is that this node must not have a left child already. If it already has a left child, then we will not add the left child to it because this will overwrite the previous pointer. If you look at the code of the function, you will see that it first asserts that there is no left child for the node pointed to by self. And if there is no left child as depicted in this diagram, then in the second line of the code, the init function of the B-tree class is called and item is passed to it. This results in creation of another node which contains item. The full line says self.lc equals B-tree item. So this happens. Pointer to the new node is placed in the LC field of the node pointed to by self. Now you can see that a left child has been added to the node that was given to us. Again, this node takes O1 time to be added to the given node. Add RC. The function adds a right child to a node pointed to by self if the node does not already have a right child. Look at this node. Again, I do not know whether this node is the right child of its parent or the left child of its parent. But I don't care about that because that is not going to make any change to my code. Also, this node may or may not have a left child. I am not bothered with that. What I am bothered with is that the node pointed to by self must not have a right child, because if I add a right child to a node that already has a right child, the old pointer will be overwritten by the new pointer, which will lead to loss of information. So the add RC function first asserts that there is no right child. Again, the B tree init function is called, which creates a new node containing item, and since self.rc equals B tree item, the right child field of the node pointed to by self now points to the new node that has been created, and you can see that a right child has been added to the node pointed to by self. This function is also O1 in time complexity. Del LC. The function deletes the left child of a node pointed to by self if the node has a leaf as its left child. It returns the data of the deleted node. Consider the node pointed to by self. We do not know if this node is the right or left child of its parent, nor does it matter. It may or may not have a right child. We check for two conditions. Condition 1. There is a left child. If there is no left child, we would not delete. The second condition is the left child which is to be deleted must be a leaf. That is, it should not have children of its own. Because if we delete a parent, we are left with orphan nodes which need to be made part of the tree again. So whenever we are asked to delete a node which has children, we simply refuse deletion. In some file systems where the tree structure is used to hold files inside folders, if you try to delete a folder which contains files, the system will refuse such deletion. You first need to move inside the folder, delete all the files, and once the folder is empty, only then you are able to delete it. Look at the code of del LC function. First, it asserts that a left child exists, and then it asserts that the left child does not have children of its own. We must recall that we mostly delete when we require data and we want to retrieve it. Before deletion, we save the value in the data structure into a new variable, and after deletion we return this variable, which is exactly what we are going to do here. So x is a variable in which we save the value b, then we put self.lc to none. Notice that there is no pointer in the LC field of the node containing a. Now we return x as the function falls out of scope. The node which was not being pointed to by anybody also perishes and falls out of scope. Again, this code is O1 in time complexity. Del RC. The function deletes the right child of a node pointed to by self if the node has a leaf as its right child. It returns the data of the deleted node. Assert self.rc is not none. Assert self.rc.lc is none, and self.rc.rc is none. X is self.rc data. Self.rc is none. Return X. Make figures to depict the execution of this code and determine its time complexity. Now we look at a function which computes the height of a binary tree. And the height of a binary tree is the number of levels in the binary tree. The function starts like this. If self.rc is none and self.lc is none, return 1. This means that if you are ever standing on a leaf, you will return 1. But if you are not standing on a leaf, then you will set a variable RH to 0 and then you will set a variable LH to 0. Now if self.rc is not none, this means if a right child is present, what do? Call the hide function within itself. This is recursion. But this time you are calling the hide function for the right child of the node. And whatever the hide function returns for the right child, you place this value in RH. Once you are done with this, then you check whether self.lc is not none. If a left child exists, call the hide function again. So this is binary recursion, calling the same function twice within itself. This time hide is being called for the left child of the node. Whatever value hide function returns for the left child, we place that value in LH. Now we have got two values, one from the right child, one from the left child. If the right child's height is greater than the left child's height, then we return right child plus 1 or height of the right child plus 1. Otherwise, we return height of the left child plus 1. Why are we adding plus 1? Because this is the height of the nodes below our node and now we are adding our node to it. Let me walk you through a trace of this function for the tree shown here. When we begin, self points to A. Now clearly you can see that A is not a leaf. So we declare RH to be 0 for A and LH to be 0 for A. Now we check the right child of A. Is it not none? Yes. So we call the hide function for the right child of A. This is the node containing C. When we call the hide function, we will pass it pointer to the node containing C. So now self will point to C. Again start from the first line of the code. C is not a leaf. Set RH to 0 for C. Set LH to 0 for C. Is there a right child for C? No. Is there a left child? Yes, the node containing F. Now we call the hide function, giving it pointer to the node containing F. Self points to F now. F is a leaf, so it returns 1. This value is placed in LH of C. Now both values RH and LH are compared at C and we find that RH is smaller than LH. So we return LH plus 1 to A. We return 2 to A. Since this value is coming from C, it will be placed in RH of A. A has just received an answer from its right subtree. So now we check for the left subtree of A. It is there and it is rooted at the node containing B. Hide function is called for the node containing B. Self now points to B. Set RH to 0 for B. Set LH to 0 for B because B is not a leaf. Check the right child of B and since it is there, call the height function again for the right child of B. Self will now point to E. RH is 0 for E, LH is 0 for E. Check the right child of E, it does not exist. Now check the left child of E and call height for the node containing G. Self is now pointing to G. But G is a leaf, so we return 1. 1 is placed in the LH of E. E has both values LH and RH. It returns the higher value plus 1 to B. It returns 2. This value is saved in the RH of B. B has just received a value from its right subtree. Now it checks its left subtree. The left child is present. Height is called again for the node containing D. Self now points to D. D is a leaf, so it returns 1 to B. This one is placed in the LH of B. B has both values now. The higher value plus 1 is returned to A. This value is placed in the LH of A. A has both values now. The higher value plus 1 is returned to the user. The height of the tree is 4. Let us talk about the time taken by the height function. The function is called for every node in the tree, and the base case of recursion materializes at the leaves which return 1. Consider the number of nodes in the tree to be n. So this means that the function is called n times, or there are n function instances which are called. A single function instance takes O1 time, and you can investigate this for yourself too. From this we can deduce that the time taken for the whole recursion is On. Now let us talk a bit about the space taken by this function. The function uses two variables and the runtime stack. The maximum number of activation records are pushed in the longest branch of the tree. The base case of recursion materializes at the leaf of the longest branch, which returns 1. The number of activation records pushed in the longest branch of a tree whose height is h is h minus 1. A single function instance takes O1 space because it uses only two variables. From this we can deduce that space taken by the whole recursion is OH. Now I have another function for you called node count, and this function gives us the total number of nodes in a tree. So the base case here is the same. If you are standing at a leaf, you return 1 because this is one node here. Then you initialize left node count to 0 and right node count to 0. And if this node has a left child, you recursively call the node count function for the left child. Whatever this recursion returns, this is placed in ln c. Then if this node has a right child, you recursively call the node count function for the right child, and whatever this recursion returns, it is placed in RNC. Then at the end of this binary recursion, you return lnc plus rnc plus 1. Count of nodes in the left subtree, count of nodes in the right subtree, plus 1. Why? Because you are counting this node as well. You will see that this function is really very similar to the height function that we just saw. Run the code for the tree drawn here and find the time and space complexity. Here is another function called leaf count. This function only counts the leaves in a tree. The base case is again the same. If you are standing on a leaf, you return 1. But if that is not the case, then you initialize two variables, left leaf count to 0 and right leaf count to 0. Now if your node has a left child, then call the leaf count function. Whatever it returns, put this value in LLC. If your node has a right child, call the leaf count function. Whatever it returns, put it in RLC. At the end of the binary recursion, return left leaf count plus right leaf count. Notice that I am not adding 1 here because this node is obviously not a leaf. Run the code for the tree drawn here and find the time and space complexity. Now we come to a different set of functions in the class btree. These are functions that help us classify our binary tree. The first one is called isStrictly binary. This function tells us whether the given tree is strictly binary or not. A strictly binary tree is one in which every node has either 2 children or 0 children, but there is no node containing just one child. We give a node to this function. It checks if the node has a left child. If there is no left child, then it checks for a right child. If there is no right child, it returns true. But if there is a right child, so now you have a node which does not have a left child, but it has a right child, so the function returns false. If the first if condition is not met, this means that there is a left child. The second if checks if there is a right child. If there is a left child but no right child, again the function returns false. If both if conditions are not met, this means that there is a left child and there is a right child. So we do binary recursion. We call the function for the left subtree. We call the function for the right subtree. We take the Boolean responses from both recursions and them. This is logical ending. And then we return the Boolean response to the function that called this function. So let us do a trace of this function on this tree. And when we begin, self points to the node containing A. So is the left child absent for A? No. So the first if condition is not met. Is the right child absent for A? No. The second if is not met. We come to the last line and the isStrictly binary function is recursively called first for the left child of A. So we pass pointer of the left child of A to the function and self now points to B. restart the function from the very first line. Does B lack a left child? No. The first if is not met. Does B lack a right child? No. The second if is not met. So the function is called again first for the left child of B, and we pass pointer of the left child of B to the function. In the new function instance, self points to D. Now look at the function and start from the very beginning. Is there a left child for D? No. The first if condition is met. Is there a right child for D? No. The nested if condition is met. So this means that D must return true, which it does. It returns true to B. Now B has received answer from its left child. Now it will recursively call the function for its right child, and self will point to E. Does E have a left child? Yes, so the first if condition is not met. Does E have a right child? No, so the second if condition is met, and E must return false. E returns F to B. Now B has received Boolean responses from both its children. It ANDs these responses and returns false to A. A receives false from its left child. Now A is supposed to recall the function for its right child and then AND the two conditions. But the first value that it has received is false, which means that no matter what is received from the right child of A, the final answer will be false. When two Boolean conditions are being ANDed and the first condition is false, you do not need to investigate or check the value of the second condition. So A returns false. And as you can see from the diagram, this is the correct response because this tree is not strictly binary. You have C which has one child, you have E which has one child. Now we talk about the time complexity of is strictly binary. The worst case happens when the tree is a perfect binary tree. The maximum number of function instances are called when we have a PBT. The function is called for every node. The base case of recursion materializes at the leaves in the last level because all the leaves are in the last level of the PBT. And the base case returns true. The number of nodes in a PBT of height h is 2 to the power h minus 1. This is from the previous lecture. A single function instance takes O1 time. And you have 2 to the power h minus 1 function instances From this we can conclude that the time for the whole recursion is O2 to the power h. Moving on to space, the maximum number of activation records are pushed in the longest branch of the tree. The base case of recursion materializes at the leaf of the longest branch, which returns true. The number of activation records pushed in the longest branch of the tree with height h is h minus 1, and a single function instance takes O1 space. So O1 space for one function instance and number of activation records are h minus 1, we can conclude that space taken by the whole recursion is OH. This next function is called isPerfect. This function tells us if the given tree is perfect or not. We know that if a tree is a PBT, then the number of nodes is 2 to the power h minus 1, where h is the height of the tree. So this is not a recursive function. Here we first call the height function, which gives us the height of the tree. Then we call the node count function, which gives us the number of nodes. Then we calculate a value called m, which gives us the number of nodes from the formula. Then we compare the actual number of nodes with the number of nodes from the formula. And if both of them are equal, then we return true. Otherwise, we return false. Find the time and space complexity of this function and write an equivalent recursive function. So what did we learn today? We implemented a class for the binary tree data structure. In fact, we are in the process of implementation. The class is not complete yet. We implemented functions to add and remove nodes from a binary tree. We implemented codes to calculate height and count nodes and leaves of a binary tree. We implemented codes to determine the type of a binary tree. Two kinds of binary trees we are able to classify now. And we examined all codes for time and space complexities. In the end, I ask you to read the book and do all the small tasks that I have strewn throughout this lecture at various positions. I have not made any homework slides here. Um, as you move along the lecture, try to do what I have asked you to do and answer all the questions that I have put up for you, because that will really help you in understanding this content. Note your questions and put them up in the relevant online session. And if you have any suggestions, email to me. Take care of yourself. Allah Hafiz.